we would like to welcome everyone to this week's STEM Talk, an online series for aerospace families brought to you by fellow aerospace experts. I'm Stephanie Parker from Aerospace University, and as part of the Aerospace STEM Talk team, we are excited to bring you this week's presentation. Now I'm going to introduce you to Patrick Yee, who is a senior engineering specialist in the fluid mechanics department. Pat mostly works on thermal analyses of cryogenic rocket engines, aerodynamic heating, and thermal protection systems. Maybe we can learn a little more about what that means today. He has supported Atlas V, Delta IV, and Falcon 9. Those are all rockets. Isn't that really cool? Now, Pat is going to talk to us about how math sneaks into our daily lives and we don't even know it, like a ninja. Pat, welcome. We are so excited to have you here with us today.
Good morning to everyone on the West Coast and afternoon to everyone on the East Coast. I'm going to start with a little video to get this presentation going. And it's basically a Delta IV launching from Vandenberg Air Force Base in Santa Barbara, California. And as you can see, when the rocket takes off, there's a lot of flame and there's a lot of burning. And as you can see, half the rocket is black. The reason I show this video is that I'm actually one of the thermal engineers that looks at the flame that comes out of the back end of the rocket. My mom told me not to play with matches when I was a kid, and I didn't listen, and now I play with very big matches. So that's kind of the quick introduction for me and what I do. And I'm going to show you that even with what I do, math is actually very simple, and it's very basic, and it's sort of things that you've already learned along the way. But before I start, what I'd like to show is that when we speak different languages, it's not universal. Like, for example, when we greet someone by saying hello in English, or hola in Spanish, bonjour in French, ciao in Italian, or konnichiwa in Japanese, all those are very, very different, and yet it serves the same purpose of basically saying hello or hi. Math, on the other hand, is very universal. And as you can see, 1 + 1 = 2, and it's basically a way of counting. And most of us probably learned to count before we actually learned our ABCs. I don't know if you recall when you were younger, but your parents probably gave you small bits of cereal or small bits of food on your tray, and they put them out one at a time so that you can grab them and eat them. And basically, you learn to count one by one each of the bits of food that you were eating. So more than likely, we did learn to count before we actually learned our ABCs. And surprisingly, that has carried forward to everyday life for us. And it's as simple as paying for something, or even just determining what time we start to do a task, do homework, go to work, go to bed, whatever. Okay, so basically, math is universal, and it's spoken by everyone, and it doesn't distinguish whether you're young, you're old, you're big, you're small, male or female, artistic, analytical, or otherwise. Math is universal because it doesn't matter, and it's something that we all do, and it's basically counting in its most basic form. If you look at a simple calculator that has 4 functions, add, subtract, multiply, and divide, basically, when you look at it, it's just basically ways to count. For example, the addition function, as you can see you have 3 red circles, and then you're going to add 3 green circles. Well, what are you really doing? You're counting the 3 red circles, 1, 2, 3, and then the green ones, you start counting from there, 4, 5, 6. So obviously, 3 + 3 = 6. But what are you doing? You're really just counting. And likewise, I'm going to do multiplication, since subtraction is probably just addition, but in the opposite direction. So let's say it's 3 times 2. So what are you really doing? You're adding 3 red circles to another 3 red circles, and once again, you're counting 1, 2, 3, 4, 5, and 6. So you're doing math, but what are you really doing? you're really just counting. And you've learned to do that at a very young age, and you consistently do it more often than not when you're not even aware of it. So on a more practical perspective, when a store says they have a 30...
We have a question.
Sure.
First, a logistical question. If you could get a little bit closer to your mic so we can hear you a little bit more clearly and make sure there's no background noise. And the material question is, are you saying that even if someone doesn't like math, they may be doing it whether they realize it or not?
Yes, and that's part of the point of this presentation, is that we all do math whether we like it or not, whether we think we're good at it or not. It's just that it's part of our lives, and that there are things around us, and we usually have to count or find some way to sort them, and math is done in this whole process. And that's why, as alluded to earlier, it's kind of ninja. We don't even realize that it's around us, and we're doing it all the time. And more often than not, most of us would consider ourselves not good at math, and math is this very abstract concept, when it really isn't. It's just a simple way of counting. Although when you do more complicated problems, the ways that you count become a little more complicated. But at the end of the day, it's still just counting. I hope that answers the question.
Yeah, that's great. Thank you. So some of us may be better at math than we think we are, huh?
Yes, and you're doing it all the time without even knowing it.
Wow. Okay, thank you.
You're welcome. Moving on, this is a shopper's paradise, a sale. Of course, we all like sales because it means we're getting a percentage off. Well, what does that really mean? Well, in a simple example, we're doing 30% off. So if I take something and split it up into 10 pieces, which are each 10%, when we say 30% off, really what we're doing is we're just counting off 3 of them and seeing how many remain. So in this case, you can see that they're 10 squares, but taking 30% off means that 7 gray squares remain. So once again, you're doing math and you don't even realize it. And oftentimes when you go shopping, you say, oh, what's 30% off? How am I going to pay for it? And how much is it going to cost? You're doing math, and you're really just counting in the whole process, even though it may be difficult to figure out what the percentages are without a calculator. But at the end of the day, it just boils down to counting. Another example is, let's say that you're going to make pancakes, where it takes 1 egg, a cup of flour, a cup of milk, and you get 3 pancakes. Okay, that's fine. Let's say that you wanted to make pancakes for your classmates if you're a child, or let's say that you want to make pancakes for your colleagues if you're a working adult. Let's say that you need to make 3 dozen pancakes. So what do? Well, basically you're just counting and saying, well, how many times are 3 pancakes needed to make the 36? Well, you'll figure out that counting, when you get to 12 threes, you'll get to 36. Well, that means that everything requires 12 times as much as what you started with. And so once again, when you basically scale or make a bigger batch of pancakes, you're really once again just counting, because there's a baseline recipe. And then from there, you just determine how many times by counting that you need to multiply it by to get the number of pancakes that you want. So once again, you're doing math and you're counting, and most likely you're not even realizing it while you're making pancakes or cupcakes or whatever you're baking in the kitchen. So I guess at this point, are there any questions? And if not, I can pose one for the audience, is how many pancakes would you be able to make if you had 100 eggs and the corresponding amount of flour and milk? So hopefully you can figure that out and type the answer, and the administrators will be able to reveal the answer shortly. Moving on to the next slide, here's something that most people love, is to have music on your portable device, whether it's your iPhone, Android phone, iPad, or even just on your PC. Well, what is that music that you're listening to? Well, on the left-hand side, you'll see that it's really a waveform that composes all the notes that are actually being played. If you just play, for example, one note, it's going to be perfect, and it's a completely repeatable pattern. But music isn't just one note. It's a combination of many notes that are played together. And so as a result, you get this funny-looking waveform that's shown on the left-hand side with the green blob. And so you say, well, how is that counting, and what does that really mean in terms of math? Well, when you look at it, if we take a very, very small slice of that green blob and expand it, what you'll see is that green blob is now actually the red line that's shown on the right-hand side. Well, what your phone or your device does is at very regular intervals, it goes and plays the height of the red curve. And so if you do it fast enough, or what they call the sampling rate, you can reproduce the red line perfectly. What's shown here with just the blue dots, it's a little coarse, meaning you don't get a perfect representation of the red line with the blue dots, but you kind of get the idea that, once again, if you just take at each given point and you count up how many lines up, and then you play the note that corresponds to that, then if you do it fast enough, it sounds like all the notes are being played together, and guess what? You have music coming out of your cell phone or your iPad or your computer, and all of us enjoy having music to entertain us when we're stuck at home as we are now. So here's another question for those who are musically inclined. We all know that notes are lettered A through G, and so the question is, does anyone know what is the frequency, or how many times the red wave goes up and down for the middle C? And we'll give you a chance to answer that, and I will reveal the answer a little later on. Moving on to something that's even more interesting and probably more relevant is, I'm sure everyone has used Google Maps to figure out how to get to a place where they've never been or don't know how to get there. Well, the thing is, Google Maps works based upon the Global Positioning System, or better known as GPS. And what GPS is a constellation of basically 24 satellites that are above the Earth, and they're in very, very stable positions that we know exactly where they are. And what happens is each satellite sends a signal out. Namely, what it does is it beeps and sends what time it is at the exact time. So let's say that we have 5 satellites, as I have in the diagram on the right, and each one of them broadcasts. It is exactly 10:16 and 2 seconds. Well, the one that comes from the blue satellite will reach the point that I have on the African continent first, because it has the shortest distance to travel. And likewise, the one that comes from the purple satellite will take the longest. So the thing is, when the blue satellite says 10:16 and 2 seconds, it'll be received by something on the ground some point in time later, and then that same satellite that's on the purple will say it's 10:16 and 2 seconds, but it actually shows up later. And our cell phones, knowing the fact that it shows up a split second later, knows how much of a difference in we are distance-wise between the blue satellite and the purple satellite. And so that kind of gives you how far you are, but it doesn't give you specifically coordinates. So the thing is, if you get a minimum of 3 satellites, you can figure out where you are in 3-dimensional space. Typically, for GPS to work well, you want 5 to 6 satellites to give you really accurate positioning so that you're not off in the parking lot of a stadium when it says that you're seated in the stadium. So basically with more satellites, the accuracy gets better. But once again, how does that relate to math? You're just counting the time that it takes the signal from one satellite to reach you, and then you're counting the time that it takes it to reach you from another satellite. And the difference, which is just plain subtraction, tells you where you are. So as you can see, all of these examples show that math is basically universal, and we do it all the time. And it's universal because we all count numbers regardless of our language. A 1 is still written as a 1, a 2 is still written as a 2, unlike hello, as I alluded to earlier, where it takes many different forms and you may or may not understand it. But with math and numbers, it's universally understood, and counting is universal. So that's why I claim that math is a universal language, and we're all pretty good at it. It's just that it may not seem that way when we are given problems that are a little bit difficult. I think that
we have a couple questions, Pat.
I'm sorry, please repeat.
Yeah, we have a couple questions. What was the question that you asked the audience? Could you please repeat the last question that you asked the audience on the music slide?
Oh, the music slide, I asked, does anyone who's musically inclined know what the frequency of middle C?
Okay, someone in the room asks, is it 440?
That's a 440. Middle C is 256.
Oh, okay.
And
then we have
440
another
is how you...
Oh, someone says it's 261.63.
Okay, that's close enough. I have in my notes as 256, but it's right around 250, give or take a little bit.
And then we have another question from someone on the line. Caitlin would like to know, if math is the basis of music, is math the basis of direction?
I would argue yes, because with direction, you're basically, I'm assuming when you say direction, you're referring to directions to go from point A to point B, not directions as instructions.
I believe that's what they mean.
With that, yes, because basically when you give directions, you're telling it to go in a certain direction, which is basically given by a compass, and that's numbered typically 0 to 360. And then the distance or directions of how far you go, you're just counting how many steps or how many miles or how many feet you are from where you started. So yes, direction is also, like music, largely based on math when you really don't even realize it.
That's very interesting. Thank you.
This was a relatively short presentation. It was really meant for 6th to 9th graders, and so it may be a little bit simplistic, but the point that I'm trying to make here is that math is universal, and most of us are pretty good at it when we don't even realize we are. And part of my giving this presentation is to encourage people to pursue careers in STEM, because this presentation was built as part of STEM outreach. And so I hope I have accomplished that.
Okay, we're just giving an opportunity for any other questions as we begin the wrap-up today. Patrick, did you have Any other closing comments on how math really is a universal language?
It really is. It's universal even for me. And yes, I work as an engineer, and yes, it appears that the rocket that I showed you was very complicated with the flame coming out the back end. But really, what I do in my day job is I actually count too. I'm just counting the amount of fuel that comes out of the engine. And basically with that, it's just like making pancakes, where I know how much fuel I dumped out into the engine, and so I can generate how much flame. So once again, even something as complicated as that rocket and as scary as it looks, at the end of the day, it's really not that different than making pancakes, as I alluded to earlier, simply because I'm just counting different things to make flame instead of making pancakes.
Well, that's a very good description and explanation, of that. We have a couple more questions.
Okay.
Charles wants to know, why do computers use binary numbers?
Because with circuits, basically, it's hard to build something that counts. And so what circuits do is there are a bunch of on and off switches. And so with it being binary, you can still count. It's just that it's counting in base 2 as opposed to base 10. So that means that instead of counting from 1 to 10, the first on-off switch is just either 1 or 0. The second on-off switch is basically the next digit, which is, so if you have 2 on switches, then it'll become 11. And so you're counting with a bunch of numbers that go 1, 0, 1, 0, but you can still use that to count. It's just that you're not counting to 10, you're counting in what's called base 2. And so it's easy to build computers that are just a bunch of on-off switches rather than building a computer that actually counts the different steps like we showed in the slide on the music wave. Because what happens is really what it's doing is it's using binary counts to count the height of the wave. And so if you realize with computers, they'll say that it's 16 bits. So that means it's really representing the value using 16 digits, which are a combination of 16 ones and zeros. I hope that answers the question.
That seems logical to me. We have another question, or a comment really, from the audience. Leo says that a friend of hers said that she had a friend who claimed that she never had to use the number pi in real life. Can you think of an example where this might be a useful thing to know?
Let's say that you are in a very practical sense. Let's say that you are wrapping a Christmas gift and you wanted to put a ribbon around it. And it just happens that your Christmas gift happens to be a tin of popcorn. I'm sure most of us have seen the Christmas tins of popcorn that are this big round thing that looks like an overgrown coffee can. Well, if we were to tie a ribbon around it, how do we know how much ribbon's required? Well, if you know how big across the tin is, and using pi, you can easily figure out how much ribbon you need to tie a bow around your tin. So, yes, you may not use pi exactly, but you'll often use it in cases where you don't even think you use it. In this case, let's say you're trying to tie a ribbon around that tin. You'll say, well, let's say it's a foot across. Well, you know that pi is 3.14 something. And so you can say, well, it's roughly 3. And so by not necessarily using pi as 3.14, even just using it as 3, you get a really good estimate of how much ribbon you would need to even just put a ribbon around a tin. And that's a very, very simplified example, but it's one that I'm sure that we've done. it may not be wrapping a Christmas tin, but we could have just tied a string around a round object. And anytime that you encounter a round object, most likely you will use pi, whether you're aware of it or not. And it usually, just as a gross approximation, 3 is a really good approximation, even though it's technically 3.14159265 ... But so you do use pi, even though you don't think you do.
Got it. Thank you. I had no idea about the tin of popcorn and using pi to wrap that. So
Right.
that is
so
very useful. And it looks like our question portion is beginning to slow down a little. Drea says we can use pi to measure our pizza as well. And that Angela says that the number pi is wonderful when March 14th rolls around. And Richard says, I love Pi Day. Yes. Seems everyone loves Pi Day. Well, Pat, thank you so much for this interesting talk on math and how it just sneaks into our everyday lives. I think we have all learned a little something here. And a big thank you to the audience, to our aerospace employees and our aerospace families. We appreciate you joining us today. For aerospace employees, you are more than welcome to enter this time into the TLC as external learning for learning credit. And we will paste a link in the chat for how to do that now, if you don't already know. We really appreciate you again taking your time, joining us with your families. We are here to support you and to listen to your ideas. And on that note, if you have any ideas for upcoming talks, if you would like to give one or nominate someone for one, please write to us at seminar@aero.org. We'd love to hear your ideas. And later today or the end of the week, this video should be posted on our Aerospace University page internally. And a little later than that, we'll be posting onto our Aerospace Corporation YouTube channel. So we would love to have you back next week. Please do consider joining us. It'll be Thursday at 1 p.m. Eastern, 10 a.m. Pacific. And we will have Jacqueline talking to us about CubeSats. We hope everyone has a great day on behalf of the Aerospace STEM Talk team. Take care, stay well, and we'll see you soon.